Hey everyone, this is going to be a very short video, but all I want to do is talk a little bit about the gravitational field, mainly because I need to make sure that you're aware of it when you see it. When you see the term, you kind of have an idea of what they're referring to. So the idea here is that we talked about how objects exert a gravitational force. All objects of mass exert gravitational forces onto each other that kind of causes them to kind of fall into each other. What we can do is talk about around those masses what the gravitational field is. The idea about this is to get a representation of how different objects might exert forces onto other masses without actually having a mass there. So we could talk about the gravitational field around one planet versus another as a way of saying that this planet may have a stronger attraction to masses than another one. So for example, we could say, oh, the gravitational field around Pluto is really small compared to the gravitational field around Jupiter. And that would make people realize that, oh, Jupiter has a much greater effect of gravitational force on masses than Pluto does for various reasons. Uh, so the gravitational field is this area around the object that exerts a gravitational force on object, and the strength of the gravitational field is g. So this whole g being the acceleration due to gravity, that's kind of actually not the appropriate name for it. It's actually specifically called the gravitational field strength. It just happens to exert be equal to the acceleration caused by gravity as well. But you might see that in certain problems where they say gravitational field strength. So here's the equation again, just taken by taking the two FG equations, setting them equal to each other. Now, one thing that we need to like to do is draw pictures that represent this gravitational field using lines. It's kind of very similar to contour lines from earth science. The way that you kind of think about it is you ask yourself, what direction is the gravitational force, or what direction would the object fall or be attracted to if I place it at these locations? So you take your object that you're trying to find the field around, you place small objects around it and ask yourselves what direction is it going to go. And if you do this, well, before I get to that, there are a few rules that you need to remember about these field lines. First thing is that the field lines never cross. The reason being is that these lines are representing resultant vectors, if you will, of the resultant of all the effects of gravity. So they should never cross, because that's the whole point of resultance, is that all the lines kind of combine into one. The gravitational field lines are always attractive because of the fact that masses are always attracted to each other. The denser the lines, the stronger the field. This is actually one of the reasons why I keep saying that they're very similar to contour lines. And that's pretty much it. So if we did it around Earth, this is what it would look like. All these lines would just go towards the Earth in a concentric circle. And then if we looked at the very close to the surface of the Earth, we would see the lines are actually fairly parallel. So at a planetary scale, at the very large scale, we can see that these lines, as they get closer and closer to the Earth, they do get closer together. So these lines become more dense as they go closer to the Earth. Further away, they're more spread apart. They're less dense. That tells me that the acceleration, or the gravitational field around the Earth, is weak when I get far away, but as I get closer, the gravitational field gets bigger and stronger. Uh, from this diagram, we could see that because the Earth, for the most part, is flat, uh, when we get really close, that is, because of this, we end up having very parallel lines. So the lines don't change in density, if you will. So here, the gravitational field is constant from small distances, that is. And this is the reasons why we can actually get away with just saying that the gravitational acceleration on Earth is 10, regardless of where you are, because for the most part, it's pretty uniform. The distance that we're getting from far away from the Earth is very small relative to how far away we are from the center of the Earth. So for the most part, the gravitational field, the acceleration, the gravitational force, all those do not change drastically. Now, this you might not see this in a lot of my slides. This virus basically means that It's not super necessary for the AP or even for the regions, but it's just something that I find somewhat interesting. Um, so what's going on with gravity? Well, in modern physics, we realized through Einstein that it turns out that mass actually warps space-time around it. So that's actually what's causing gravity is not necessarily the attractive force between masses, but more that the space is being kind of warped around it, very similar to placing an object onto a trampoline, how it kind of dips the trampoline down and then all the objects will start to fall towards it. And the more massive the object is, the more space time gets distorted to the point where it's actually even able to bend light. This is actually how we know that space is getting distorted because light will actually bend around masses. Now, again, this is only really observable when we start talking about very massive things. I don't even think it can be seen around planets. Stars sort of bend light, but it's really mostly with galaxies where we start to really see the bending of light in a lot of cases. In fact, the image of the black hole that was recently found uh, was caused by the weird bending of light around the black hole. And that actually leads me into this comment about black holes and how that we can actually get to the very extreme where if the gravitational field around an object is strong enough, not only will it cause light to bend around it, but it can make it so that light will actually never pass through it, where light will actually go into it and not be able to escape. And that's kind of what a black hole is. Black hole has such a strong gravitational pull that it bends space so much that light is not fast enough to get out of it. There's a variety of different ways that they can phrase this. And a lot of really weird stuff happens when you start getting close to black holes. Um, of course, a lot of this stuff is somewhat theoretical since we can't really do a whole lot of testing on black holes. However, the science kind of fits with what we are seeing with a lot of other stuff. I recommend watching a bunch of videos on this because the black hole stuff is super interesting. And that's pretty much it. Honestly, with the gravitational field lines, it's really basic. Again, it's the equation that I had shown you before, plus this idea of drawing field lines around stuff. And that's it. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.